All right, we're going to look at two more examples today using integration by parts. This example is a really interesting one because we'll see that we end up needing to do a few extra steps here. So again, we want to choose for dv something that's easy to integrate, or we want to choose for u something that's easy to differentiate. So what I chose was I let dv equal the cosine of x dx. So when you integrate both sides, that tells us that v is going to be the sine of x. And I let u equal x squared, so that means that du is going to be 2x dx. Remember that one of the other goals we've talked about is wanting to choose something for u that gets simpler as you differentiate it. And this is a perfect example as to why. So we're going to come over here and do our u times v minus the integral of v du. So u times v is going to be x squared times the sine of x minus the integral of v, which is sine, times du, which is 2x dx. So this becomes 2x sine x dx. Now, think about how we could integrate this second one. You could try u substitution, but it's not going to work. What we've ended up here with is something that we need to do parts again. So we have to use parts again on this one. So I would set this up very similarly. I'm going to let dv be the sine of x dx, and that would make v equal to negative cosine of x. And I'm going to let u be 2x. That makes du 2 dx. So again, see what's happening here is that each time we do our integration by parts, that polynomial term, the x squared, is dwindling down and dwindling down to where now we've ended up with a constant, which is going to make this much simpler for us to work through. So if I apply integration by parts again, I get x squared times the sine of x, that's what we had, minus, now we're subtracting this whole integral, so you have to make sure you put it in parentheses because this integral is now going to become two pieces, and we need to make sure that we're subtracting them both. So once again, this is going to be u times v, so that's going to be negative 2x cosine x minus the integral of v du. So that's going to be negative 2. So I'm going to make this, well, we'll just leave it all together. Negative 2 cosine of x dx. Okay, so now we're left with something here, cosine of x, that we can integrate. By choosing u strategically, we were able to differentiate it down to a constant, and that's what allows us to finish this integral here at the bottom. So we have x squared sine x. This is now going to be plus 2x cosine x. And we're going to have when we distribute the negative, we get plus the integral of negative 2 cosine x dx. But then we have the negative, which is going to make it minus 2. And the integral of cosine is sine of x. And that we're done now, so that's going to be plus c. And so that's what we get when we integrate that function. It ends up pretty gross, but it works just fine. So the takeaway here is that sometimes you might need to use integration by parts more than once. Now, the next example we're actually going to skip just in the interest of time. This is an interesting example, but it's definitely more advanced than the scope of this course, I think. So for the sake of not spending too much time on this, we're going to go ahead and move on. But I will post the notes on this. I will warn you, it took me about a page to work this problem out. You get stuck in a loop, which causes an interesting dilemma. And so if you want to take a peek at that and see how you would solve that problem, then I will post that for your own curiosity. But this is beyond what I would test you on, and this is beyond likely what you would be tested on the AP exam. So let's go ahead and go down here to example 6, where we have a definite integral that we need to use integration by parts. So this is very similar to the previous one, and your instinct might be to let u be x cubed because it's the polynomial piece. However, that would mean that dv has to become the natural log of x. And we don't really have a rule for the antiderivative of natural log of x. You could use integration by parts to do it, but that is kind of defeating the purpose of doing it now. So that's how I would come to the conclusion that what I actually want to use is I want to let u be the natural log of x. And that means that I want to let dv equal x cubed dx. So du then becomes 1 over x dx. And v, if we integrate this, becomes x to the 4th over 4, which may not feel like it's getting better, but we'll see how this ends up working out. So now we want to set this up. It's going to be the same thing. It's going to be u times v, but remember that u times v came out of this definite integral from 1 to 2. So it's going to essentially be this. We're going to do u times v, and that has to be held off for the definite integral from a to b, and now this is minus the integral from a to b of v du is how we have to treat this. We don't need to adjust our limits or anything because the whole point of integration by parts is that we're going to replace the u and the v. We're not going to leave it in terms of u and v, so we can stick with our original limits of integration from 1 to 2. So u times v is going to be 1/4 times the natural log of x times, what are we doing? X to the 4th. I lost my train of thought there for a second. And that we need to evaluate from 1 to 2 minus, now we want the integral from 1 to 2 of v, which is x to the 4th over 4, times du, which is 1 over x dx. Now, inside here, this works out kind of nicely because one of these x's is going to divide out, and we can pull out the 1/4. So this second half here ends up being 1/4 the integral from 1 to 2 of simply x cubed dx. And that's something that we can certainly do. So for this u times v piece that we pulled out, this is going to have to be 1/4 natural log of 2 times 16 minus 1/4 the natural log of 1 times 1. Well, the natural log of 1 is 0. If that is not something that you immediately recognize, put it on a flashcard because that's a freebie when you get a natural log of 1. That whole expression is going to be 0. And so this becomes 4 times the natural log of 2. And then over here, we now have 1/4 times, this is going to be x to the 4th over 4 from, again, 1 to 2. Whoops. All right, so let's finish this out. 4 natural log 2 minus, this is going to be 1/4. Actually, I'm going to go ahead and pull out the 1/4 that's inside. So this becomes 1/16 times 2 to the 4th minus 1 to the 4th. So 2 to the 4th is going to be 16 1 to the 4th is going to be 1. So the answer we get is the natural log of, or 4 times the natural log of 2 minus 15/16. And again, that's a perfectly acceptable answer. So we could stop right there. And so that is it. Just make sure the biggest thing that people miss on these is forgetting to evaluate the u times v. That came from the original integral, so it needs to be evaluated. And that's how you can do the definite integral with integration by parts. Again, you can check out example 5, which will be posted on Canvas if you are interested in that. And I will see you next time.